Okay, so we're on proposition 11. I keep being inconsistent about this. I'm proposition 2.11, and this is interesting. This is the golden ratio. I'm going to write it in golden ratio. So what Euclid does is actually to construct the golden ratio using just Euclidean geometry. And this is something that I haven't seen before. I've always just, had it taught to me as a solution of a quadratic equation. But we can see that here, even if you don't know about solving quadratic equations algebraically, you can nonetheless still construct the golden ratio in a very simple way. So in the usual Euclidean style, he'll tell you how to do this, and you have to kind of figure out that, oh, that's actually what he's doing. So to cut a given straight line, so the line will be AB. So we're gonna draw it like this. Okay, so this is the line AB. Okay, so we're going to cut it at a specific point, and that point will give us the golden ratio. And I'll explain where the ratio part comes from. So this is a straight line. I guess this is AB. Let's indicate that so that the rectangle contained by the whole line by the whole line and one of the pieces so this is just going to be AB times, we'll mark it in later, is equal to the square on the other piece. Is equal to the square on the other piece. Okay, so maybe I haven't left enough room to do this diagram, but we'll attempt to do this. So basically, we want to find a point H on this line, yet to be determined, such that I guess we can mark it in the rectangle, the whole line, one of the pieces. This is AB cross BH. Okay, now that we have a notation for this point, and the other square on the other piece is going to be AH squared. Right. Okay, so you can already see that we're trying to solve a quadratic equation because there's an AH in there. And I guess AB times BH is another quadratic term, and they have to be equal. So you can already see kind of what's going on. But let's not think about this algebraically and just do this geometrically. So the first construction we're going to make, unsurprisingly, is we're going to construct a square because this book is all about squares. So we're going to draw a square on AB like this. Kind of just fits here. So this is our usual proposition 1.46. All right, gives us a square on AB. Okay, and we're going to label the points as well, A, B, C, D. Right, C, D. And the next thing we're going to do is we're going to draw a midpoint on AC. So we're going to label a point here called E. Right? And this is going to be a point on AC such that it cuts it in half. And the proposition that allows us to do this is proposition 1.10. So proposition 1.10 gives us, I guess I'm just going to write midpoint E on AC using some modern terminology. Okay, so now we're going to join this point with B. Just going to draw them, give me a triangle. And the next thing we're going to do is we're going to extend the line CA like this. Just going to extend it. Probably going to be running into the words there. Hopefully, it's not so bad. Extend this line AC like this, and the point here is going to be called F, and I have to tell you how far we're extending it. This is not an arbitrary point. This is I'm going to erase this AH squared and stick it somewhere else, so we're not crashing into ourselves. AH squared. Okay. Right. So this thing here, we're going to extend this such that EF is equal to BE. So we're going to do this such that EF is equal to BE. And the proposition that gives us, allows us to do this is an early one, 1.3, tells you that you can extend a line for any given length, right? So I can extend the line, I guess, EA to any given length, and the length we want is that EF is equal to BE. Okay, and then the last construction we're going to do here is that we're going to complete, well, we're going to draw a square on AF like this. The last thing we're going to do, or maybe not the last thing, second last thing, I'm going to draw a square on AF. Kind of just fits. A square like this. And we're going to extend this line.
Wait, why does that meet H?
Oh, I've done this kind of backwards, right? H is as yet to be determined, right? So I
wait. No,
drew it on the...
Oh, I see. Okay. Wait. Oh, so to cut a given straight line. Okay, so now we define H to be where that is. All right.
Right. I was slightly confused when I read it as well.
But
so H,
But what's this horizontal line you've drawn out from F? How long is that? Where does that length come from?
That length is coming from EB. So this length here is equal to this length here.
Yeah, I get that. That defines F, but then you've drawn this line. Right. You've drawn a square, but that's a square. I see. It's a square on AF. Okay.
Yeah.
So AH is equal to AF. Yeah. Okay, I got it.
Right. Yes, it takes a little bit of thinking, because usually with Euclid, I think this is the first time we've defined a point by a bunch of geometric constructions, right? Previously, we make some constructions, we're proving a general statement about the configuration, and that's maybe that's not true, right? Like, previously we would have done like proposition 1.3 is kind of defining the point F given a length, in this case EB. But in that case, it's very simple. You say, well, just drawing the line out that far, you draw a circle, and there you go, right? But here, H wasn't given a name. Anyway, I kind of gave it a name too early, which maybe gave us the impression that H was arbitrary, but it's not. So this construction, when we got to the end, is the definition of what H is, and we're going to prove that it has the property that we want, which is that which is the statement of the proposition. And so the last thing that we did here was to extend this line. This is actually a line here, not it goes right through, so it just hits the line CD at K. And so all these, we've got two squares, right? AD, and I guess we missed labeling a point. This is G, and FH, they're both squares. So, right, and let me just, I'll come back to the golden ratio stuff later on, but at this point, at least it's not clear to me that we're talking about the golden ratio. I had to stick some algebra in there to kind of see it.
I didn't recognize this connection when I read the proof, yeah.
Yeah, it was just kind of like, well, this is a cool point that we found. Like, okay, great. But that's we'll fill in the algebra later so that we can recognize for it for what it is. But let's go through the proof quickly, and then we'll give the interpretation.
I
So the
think,
first thing,
sorry to interrupt, but I think you twice might be a bit skeptical. It says there's different
uh,
versions of history surrounding mathematicians attempting to square the circle. It reminds me that in mathematics, as well as technical excellence, we have to also maintain basic competency and vigilance regarding practical matters. I think he's accusing you of being a fraud, Kenneth.
wow. And I kind of indirectly accusing Euclid of being a fraud. That's hilarious. So where was I? So we're gonna apply proposition 2.6. Maybe this is the first time we used a proposition from two.
Yeah, that's
We've
right.
used a lot from one, and so
Yeah.
we're actually now using a proposition from two. And of course, I don't remember what this says, but I think by the time I write this out, it'll be clear. So we're gonna apply this to AC, and AC is well, AC is one side of the square, left hand side of the square, bisected. So when we read proposition 2.6, it was kind of a specific thing. We all wondered, why are you doing this, right? But here, oh, not just 2.6, 2 point, you know,
Yeah.
the other 2 point, small numbers, right, around there. And I guess here is a direct application of 2.6, which is kind of cool. So we're going to apply this to AC bisected at E, right, which is what we constructed E to be, and extend it to F. And I think this sentence is a little bit strange, but we have to kind of look at 2.6 to see why I'm kind of saying like this gives. So I'm going to go back to the diagram here and label some stuff. I'm going to give it some. I'm gonna I'm gonna do some algebra. Sorry. So I'm gonna call this distance B, and so then FG is B, AF is B, and I'm gonna call this distance A, right? And so this is the midpoint, so this distance here is gonna be 2A, and this whole distance here is gonna be 2A plus B. And I'm gonna refer to the kind of the algebraic version of 2.6 to tell us what the conclusion is, right? So remember, uh, the algebraic version of 2.6 is 2a plus b, where a's and b's are what I've labeled, right? These are not just arbitrary things. I've matched up the a's and b's with how we're going to apply the proposition. So this gives us a good way to just see what the conclusion is, right? So, well, that's the conclusion, and we're gonna just write this in terms of the labels of the the names of the lines, right, rather than the algebraic, the letters, the lengths. So this is just a mnemonic to help us figure out what's going on. So, okay, so this is actually going to be CF cross FA plus AE squared equals EF squared. Okay, so starting from the left-hand side, is CF is the whole length, right? The drawn to A plus B is the length of the small square plus the length of the big square. B is FA, which is fine. We labeled it B. AE squared is AE squared is A squared because we've labeled AE as small a, and EF squared, EF is the, well, EF is B plus A, and so, yeah, because EF is the half of the big square plus the, well, half of the side of the big square plus one of the sides of the small square. So this is just literally translating what 2.6 is in this diagram. And so now we're going to do some algebra. We're just going to make is equal to EB squared. Now this is, since this is kind of stupid, right? EF is equal to EB. By construction, all right, with construction, made them equal in virtue of the diagram. So now we're going to do Pythagoras' theorem. So we're going to apply proposition 1.47. So we have to use Pythagoras' theorem somewhere to the triangle AEB. Okay, and so EB is the hypotenuse of the triangle AEB. So this gives us AE squared plus AB squared. And now we're just going to take away AE from both sides. And this seems like the kind of algebraic like subtraction that we've done before, right? We're adding up a bunch of squares, and we see the same term appearing on both sides, and we're just going to take him away. So we're going to subtract. So this is very much like doing algebra. AE squared from both sides. Right, and this gives us CF cross FA is equal to AB squared. Okay, so we're almost there. This CF cross FA, right? This thing here is really just the rectangle FK, and the rectangle FK is I'll just draw it in here. That's this thing here. Okay. And on the other side, on the right-hand side, since FA is equal to FG, FA, that looks like a P. There's no P. FA is equal to FG. And on the right-hand side, this is the square on AD. Or not on AD, this is the square AD. AD is it's just the name of the square, I guess. Right, going back to the diagram, AD, yeah, that's a big square. Right, and so now I'm going to go back to the diagram and just indicate what's going on here. So we've said that this diagram, this shaded region is the same as this shaded region. And so what we're going to do is just going to subtract AK from both sides. And this subtraction is, I think, is a geometric one, right? We've got shapes stuck together, juxtaposed together, which is going to remove one part of it, just like how we constructed the Neumann. And this will tell us that the remaining parts are then the same. And so that's what we're going to do. So now we're going to subtract. We're going to subtract. We're going to subtract the AK from both figures. And this gives us, I guess this will just fit, right? To gives the square FH is equal to, that's bad handwriting there, FH is equal to the rectangle HD. Going back to the diagram, this then says that these two shaded areas, find the right color, these two shaded areas are then the same. And we can see that this is exactly what we wanted to prove from the beginning, which is that this FH here is, I'm running out of space a little bit, but this is AH squared. And this thing here is AB cross BH. Okay, so that's the end of the proof. So we've verified that by using Pythagoras and kind of putting, subtracting and adding things together, subtracting them, we've gotten that these two are the same. So now, yeah, when I got to the end of the proof, I was like, what did we just do? And so Um, so I'm gonna go and label this length. Well, this length is b, but I'm gonna call it x, just because it'll make it a little bit easier. So this length I'm gonna call x, which is b. I'm gonna call this length 1, just normalizing it to be 1. And so if we write down what the algebraic equation is here, you see kind of what's going on. So this here says that x squared is equal to x plus 1 times 1, right? This is just x squared is just the area of the square fh, and x plus 1 is x plus 1 times 1, which is the area of this rectangle here. And of course, if you solve x, because h is constructed such that these two quantities are equal, if you solve x, well, you already know that this gives you the golden ratio, because this is the quadratic equation that well, where we first learned this, right? I guess most of us learned it like this. And so yeah, so that's the construction that gives it to you. There's a footnote that kind of expresses this as a ratio, because still, this is still not clear why it's called the golden ratio, right? It's just a solution of a quadratic equation. So the golden ratio, I'll write this as a thing on the last board, but maybe I should walk over so we can see
Wait,
this board.
there's two roots of that equation. Why is it 1
Yes.
plus root 5 on 2?
Yeah, so I think this one gives you the 1 plus root 5 on 2, not the other one. The other one's negative, right?
Yeah. Oh, right, of course.
Yeah.
Yeah, sure. That's cool.
So, yeah, so the last thing I'll say is the ratio stuff, right? So the golden ratio, this is the footnote in Euclid. This is the golden ratio. And like you said, like this is probably something that predates Euclid, and I kept writing golden ration.
Yum.
Yeah. So this is the ratio of the whole piece over the larger piece is equal to the larger piece.
Wait, what's the whole piece and larger piece? The
Oh,
whole is
I
not.
guess I'll write out what it is. This is just the smaller piece. I mean, this is just some dumb way of saying, the whole piece here is, you cut it like this. The whole piece
Oh, it's
is
made up of a smaller
one,
piece and a larger piece. Okay.
x one, right? And
Yeah.
so like x is the larger piece, right?
I see.
And so you get exactly what you write. X plus 1 over x is equal to x over 1. So this gives you the same quadratic equation. So that's where I guess this is the definition of the golden ratio. If you have a piece of something, you cut it in a way to make two unequal parts, right? And such that this ratio is satisfied, then you've cut it in the golden ratio. And where you should cut it is at x, where x is the solution of this equation.
I wonder why he didn't state that in the proposition. This seems like a more Euclidean
Yeah.
statement than the thing he said.
Yeah, right. Yeah, maybe it was. I mean, I don't know the history of this, right? But maybe it's he's doing the same thing as the golden ratio, but he's kind of doing it in a different
Ah,
way.
but of course, no, he is saying that. He just can't say division, right? I mean, if you rearrange that
Oh,
formula, it is the statement. Yeah, okay.
So this is a question about like doing this kind of construction, right? So using Euclidean geometry, we've solved a particular quadratic equation, right? Can we do this? Can we do this for any quadratic? Like, you write down some quadratic equation, and can you draw some squares and triangles using Euclidean geometry to give you the solution? I think you can, right?
It's just a question of completing the square, so must be.
Yeah.
We must be getting to that at some
Right.
point. Yeah.
Yeah, so it should be some general method that you can just do this for all the quadratic equations at least. So yeah.
Hmm. Yeah, interesting question. Yeah, I don't know. But that was cool and non-trivial, right? I mean, once you have proposition
Yeah.
2.6, I guess maybe it's fairly easy to see what to do, but the structure
Mm.
here is you had to if you didn't have anything in book 2 and someone just told you to prove this, you'd have to think a fair bit, I think.
Yeah, if you only allowed to use Euclidean geometry, you're kind of, well, you'll be drawing lots of constructions to try to get it out. Eventually, something like this, right? But yeah, 2.6. I wonder if 2.6 was written with this in mind,
Of
right?
course,
We're
yeah.
gonna apply this, right? That's why it's a bit weird.
Yeah,
The way we
it's
think, well, this is stupid. Why would you do this? But here
yeah.
we here we go.
So
It
this
works.
this tradition of mysterious lemmas that the students have no idea what they're for, being finally revealed after weeks and weeks to be important for some theorem at the end of the semester is truly ancient.
Yeah, right. This is we all went through this, right?
That's great. Okay, any questions? You twice was very impressed by the golden ratio. I think it's part of his. He's got some history
Yeah,
of Greek mathematics that he's
yeah.
referring to, and it's all over that, I'm sure.
Nice. He didn't
But
walk off this time.
no, that's right. You were interesting this time. Well, he could actually hear you this time. Last time I didn't have the transcription working,
Oh, oh, I see, I see.
so he got bored. Any questions for Kenneth? Comments about the beauty of Euclid? All
Yeah, I
right.
think this is my favorite proof in book two so far.
Yeah, yeah, me too. I mean, I liked the one we did last time, but it still had a bit of a routine flavor. This was not so much routine stuff. It sort of felt like
Yeah.
everything we did was kind of interesting. Yeah.